All right, so we are going to go through this static equilibrium example 3. One of the things to note about this problem is it might look more complicated than some of the ones that we've done before because of the pulley contraption. It's actually a lot easier. So let's just go through the problem real quick, and then I'll discuss the hint for the homework assignment that's due on Monday. So we have this collar that's sliding along a pipe or a frictionless rod, and the idea is to determine whatever the magnitude of the force P is required to keep the rod or to keep the maintain equilibrium of this collar at point A. Now, so first off, before we do anything, let's handle the trig. So we know that we've got this right triangle here, and we know that this is 20 inches from the height. Ultimately, what I'm trying to do is figure out this angle here, this angle theta. So that's this right here, and we were told in the problem that x is 4.5 inches. The whole point is to find the force required to maintain equilibrium when that distance is 4.5 inches. So what we can do is, before we even do any free body diagrams or anything like that, we can say that theta is the inverse tangent of 4.5 over 20 inches. Okay, and that should be pretty straightforward. When you chug that out, you will get, oh, no, sorry, that's backwards. Opposite over adjacent. I'm sure somebody who's watching this on YouTube was like, oh, no, that's wrong. All right, so this is 77.32 degrees. So when we draw our free body diagram for point A, we can handle that pretty easily because we've already got that figured out. So let's look at the free body diagram. So if I scroll down a little bit, just to give myself a little bit more room, here's the point right here. And what we have is a horizontal force P, like that. And then I'll use blue for the cable. We have a cable that's going like that. Okay. Now, the force inside that cable, we'll call that tensile force T. I think the best way of describing T would be the tensile force times the cosine of the angle times I, plus the tensile force times the sine of the angle times J. Now, just because, well, let me say it like this. We haven't yet determined what T is, although it's pretty obvious from the free body diagram. Because we referenced our angle from the horizontal, this should sort of be a default approach to how you draw or how you describe your vectors. Just in 2D. Once we've got our angle from the horizontal, cosine times I, sine times J, and throwing the magnitude in on both terms. Now, in terms of the magnitude, it should be pretty apparent from our diagram that the tensile force in the cable or in the rope is 50 pounds. Because when we look right here, we have a 50-pound weight hanging off of the end of the cable. So if the weight is pulling 50 pounds down, the cable has to resist with 50 pounds up. So the tensile force inside the cable is 50 pounds, and it's the same tensile force inside all the points along the cable. So that means that the tensile force is 50 pounds. Plus, and then okay, first thing, but before we move on, are our signs correct? Yes, they are, because we have positive x direction, positive y direction. Signs are correct. Now, one thing I do want to mention before we move on, this free body diagram is actually incomplete, and I'll illustrate that in the end. But for the purposes of what we're doing for this problem, it actually doesn't matter that it's incomplete, but I'll show you why it's incomplete here in a bit. Okay, let me scroll this down. Okay, so if I chug this out, I get, let's see, I actually didn't do that, but that actually doesn't matter. But let's do that over here on the side. You'll like what I'm going to do here. There's our Casio, 50 times cosine bam. So that is, let's see, 10.98 plus I gotta click this. So there you go. Now, as for the p vector is just negative p times I. Right? That's all that is. So if I'm summing forces in the x direction, I just sum up all the components associated with the I vector. So I have negative p plus 10.98 pounds. And that's it. That's all there is to it. So hopefully that should be pretty simple from a conceptual standpoint. Now, before we move on to the homework hint, one of the things I did want to just make sure that everybody's clear on is that, again, this free body diagram is incomplete. Okay? And the reason why it's incomplete, and the easiest way to see why it's incomplete, is to look at sum of forces in the y direction. Okay? If you look at sum of forces in the y direction, what you see is there's 48.78 pounds going up, but there's nothing going down. There's no additional component. What I propose is that if you go back to the basics of the problem, go back to the initial problem description, this collar is sliding along this frictionless rod. And look at what's happening. So the weight is going like this, okay? That weight is going to pull up on that rod. Because the rod is not moving, the rod is resisting that going down. Now, we don't need to determine that. That wasn't really the purpose of the problem. But if we wanted to know how much the rod is holding it down, we would do sum of forces in the y direction, and we would get 48.78 pounds. It's not necessary for the purposes of the problem, so we don't need to do it. But it is worth mentioning that there has to be something holding it down, otherwise sum of forces in the y direction wouldn't be zero, and we wouldn't be dealing with a static situation, we would be dealing with a dynamic situation. So make sure that you're accounting for that, at least conceptually in your head. Wasn't necessary for this problem, but did want to bring it up. Okay. Homework 2.5 hint. And I am sure right off the bat, this problem looks scary. It's not, okay? What I want to do is show you what's going on with the free body diagram. If you understand the free body diagram, you will understand everything that you need in order to assess this problem. So, the first thing to note is that there is a vector P going like that. Okay? There's your angle alpha. And based on the textual description in the problem, you can determine alpha. That shouldn't be an issue. What else? There is a vector going down. And the vector going down is the box's weight. Okay? Keep in mind, weight, not mass. Finally, there is a vector going this way. Now, before we talk about the magnitude, if you will, you should be able to determine that angle based off of this measurement and that measurement pretty easily based on what we've done so far. That should be pretty straightforward. But what about the magnitude? Well, here's the deal. Cables or ropes, whichever you want, cables, ropes, pulley problems in general, the assumption is that the force in the cable is consistent throughout the cable. Okay. Now, this is a static particles problem, so we're going to assume, I know it looks like those cables are separated by a distance, like you see right there, but we're going to assume that those are all lumped on one point. The idea is that there are two cables, so that vector is 2p. This is your hint for the homework. Is basically the free body diagram. That you have the weight vector going down, you have p going up and to the right, and you have 2p going up and to the left. That is enough information to solve for the required force p in order to achieve equilibrium. All right, that's all that we have for this lecture. One of the things I am toying with is, because of all of the technological problems that we had in class today, I'm thinking about recording an additional video where we go through the problem again in class, just to ensure that the audio records appropriately and that all the calculations are a little cleaner. And I might do that here in a bit. But I wanted to get this posted or get this recorded and posted as soon as possible so that you were prepared for your homework assignment. That's all I have. Hope you all have a wonderful weekend. We will see you all on Monday.